Hello, dear students. Today I am taking a new topic. The topic is moving coil galvanometer. See carefully. The topic is moving coil galvanometer. So first of all, you have to know what is the galvanometer. Galvanometer. What is the galvanometer? Galvanometer is a device. Galvanometer is a device which measures the current. Basically, this used for the measures the current, but later it converted to also to measure the voltage. But galvanometer works on which principle we have to know. See, there are in the previous video we studied about the magnetic torque, means torque produced by the magnetic forces. The same principle theory is used in the galvanometer. See, galvanometer mainly has two parts. What? One is coil and other is magnet. See in device, one is magnet. See, NS is magnet, also magnet is there, and another is coil. This one is core, or you can say this one, this indicated the coil. So this is a coil. In this coil, core is inside part. Okay. So there are main two parts. First part is coil, second part is magnet. Now, out of these two parts, if the magnet is moving or core is moving, the name of galvanometer will be as per. If coil is moving, then it is called moving coil galvanometer. If magnet is moving, then moving magnet galvanometer. Means galvanometer are two types. What are their types? Moving coil galvanometer and moving magnet galvanometer. The moving magnet galvanometer not in your syllabus. Only the moving coil galvanometer in your syllabus. It's okay. So let's close it and now see the next. Since the coil is moving between the magnets, so this is called the moving coil galvanometer. And now see now about the moving coil galvanometer. So first one is a magnet. This magnet also magnet, and north and south poles are fixed here, and in between the poles a uniform magnetic field is there, and in this uniform magnetic field a core, you can say a coil. This coil consists of core. This core will be a soft iron core, and soft iron core in aluminum frame. Soft iron core within aluminum frame is hanged here. Means you can say there is a one wire which is attached to this one. Okay, hang to this one. Now see what happens here. When current is given to this core, and inside there is a spring. This one is a spring. When current is given to this coil, plus and minus, then what happens? Then a current flowing coil is kept in the magnetic field. You got this lesson, that when current flowing wire, a current flowing circular loop is kept in magnetic field, a torque is produced. What is the torque? Means one force is acting this side, one force is acting this side. Means two equal and opposite forces are acting in the coil, and they rotates the coil. When torque produced, coil rotates, and coil rotates clockwise. Then what happens? This indicator, this one is a indicator. This one is the indicator. This indicator moves this side and reaches to the maximum scale, and we can note the value of the current. Okay, so First of all, what happening here? Inside the uniform magnetic field, this magnet is fixed. In this uniform magnetic field, a coil is suspended. This coil consists the core, soft iron, and one spring attached indicator. A scale is here. This is a scale. And now see, when the current is given to this coil and the current produces a equal and opposite force, that is torque in the coil. Coil tends to rotate, and when coil rotates, the indicator attached with this spring also moves in this direction. And here see, if we will change the polarity of the current, the indicator moving in this direction will move in this direction. Why? The torque produced in the previous case is clockwise, and we will change the polarity of current, the indicator will move anti-clockwise. Why? Because torque will change now the anti-clockwise. Yes, there may be the two type of the rotation. For example, if this one is a and force acting, this means clockwise, and if force acting from opposite direction like that, means torque may be in the two direction. Rotation may be in the two direction, clockwise and anti-clockwise. If rotation is clockwise, if rotation is anti-clockwise, it depends on the force acting. Okay, now see, now we will see some expression. See, this is a south pole. So when the current is given, the torque is produced, and this torque is called BINA. You know, this torque is produced in the coil when we are giving the I current to this coil. When we are giving I current to this coil, the torque is produced. We read in the previous video. This is very clear. What are the values here? Tau means torque, B means magnetic field, I means current given, N means number of turns, and A means area of coil. For example, here coil is circular, and in the previous video we read the coil was rectangular. Here coil is circular. Here coil is circular, and in previous video the coil was rectangular. So here area will be the pi r square, and n is the number of turns, means how many wires are here rounded, AR winding is done. So this is called the number of turns. I means current. Okay, this is clear. And now we know that torque is directly proportional to theta. Torque is directly proportional to theta. What is here theta? Theta is the angular displacement. See, torque is equal to C theta. Here C is the torsion constant. Torsion constant of this spring. C is the torsion constant of this spring, and as much torque produced, as much displacement indicator will take. This says as much torque produced, this indicator will move as much. Theta means increases. As torque produced, the deflections in angular displacement also increases. So proportionality constant is here theta, and C is the torsion constant of this spring. The material of spring will be different to different. If this is silver, if this is a steel, if this is any other alloy, then the value of C will be the different. So now here two equations are here. Equation 1, equation 2. Now see, make sure very clear, C is a constant, spring constant, torsion constant, theta is the displacement. What displacement? Indicator. This. Now combining both, comparing both. Now comparing both. See carefully. When we will compare, then you will get BINA equal to C theta, or I equal to C by ban into theta. So this is the final formula, and this value Cy band, this is a constant. So again let this is a constant, A equal to Cy band, then I equal to K theta. Generally I is directly proportional to theta. This is the principle. This is the principle of the galvanometer. What is that? Current will be directly proportional to the deflection, means as much current you are giving to the coil, as much deflections you will get. So current is directly proportional to theta. This is one concept. This is called the principle of galvanometer. Now see, the detailed theory, actually there was given some more factors in your previous syllabus, but now the syllabus is syllabus modified, and so that's why also I am modifying our video. So only up to this one. After that we will see one more word, that is called current sensitivity. That is called current sensitivity. What is the current sensitivity? Let's see. Current sensitivity. Current sensitivity of the galvanometer. Current sensitivity is defined as from this formula, means theta per unit current. Current sensitivity theta per unit current. This is called SI, means current sensitivity. Current sensitivity is denoted by SI, and this SI is equal to theta upon I. Now you can write here theta upon I from here. Current sensitivity, this is equal to band by C. Band by C. This is the current sensitivity. Theta upon I is called the current sensitivity, and you generally SI you write band by C. This is the current sensitivity. Now tell me, the current sensitivity depends on what factors? Current sensitivity depends on magnetic field, area of the loop, number of the turns, and the nature of the spring, which type of spring is used. And now if we will convert this current sensitivity in the voltage sensitivity, then what happens? Voltage sensitivity. Now see, voltage sensitivity, this is SV is equal to theta upon V per unit voltage. So you write here theta upon V equal to IR. So you theta upon I is here given. So band by CR. Now tell me, here voltage sensitivity depends on resistance also. Voltage sensitivity is inversely proportional to the resistance, but current sensitivity does not depend on the resistance. Make sure. The voltage sensitivity depends on the resistance of the coil, while the current sensitivity does not depend on the resistance of the coil. So these are the two terms used in the moving coil galvanometer. First is principle working, and then this one current and voltage sensitivity. Some questions given in your NCERT textbook, question number 4.78, 4.9, 2-3 questions are given on these topics, so you will solve them. Okay, now one more question, one more topic from the moving coil galvanometer: conversion from galvanometer to ammeter. Now see, what is the ammeter? Ammeter is a device which measures the current. Galvanometer can measure both. So how it can be converted? What it says, that when a galvanometer is this one, and in the parallel to galvanometer a low resistance sensing done. See, this happen. This is the total current. If total current is high, then reduce the current by connecting another parallel resistance. then what happens? Here the value of current becomes less. Now see, so how we can convert galvanometer ammeter into ammeter? When low resistance, here low resistance is yes connected with parallel of galvanometer. Galvanometer. What is the resistance of galvanometer here? G. So now see what happens. Let this one is I is the total current passing from this wire, and you know when there will be current more than limit or more than range, what happens? The indicator of galvanometer can break the scale, so that's why a parallel shunting is given here. This is also called shunting. Yes is the low resistance, it is connected in parallel. This also called shunting. This one what is called shunting. So what happens? This converts into the ammeter. Generally, what you had saw that this is a scale, and this one is indicator. This one is a magnet. So here in the parallel of this one, a low resistance S is connected. This is the ammeter. Okay. Now, how the galvanometer converted into voltmeter? How the galvanometer converted into the voltmeter? So, galvanometer converted into voltmeter only by changing in series. Let this one is galvanometer, and here another resistance connected in series, means high resistance connected in series. Very clear, connected in series. Then galvanometer converted into voltmeter. See, here I current is going, same current passes, series, and this R is high resistance. This is galvanometer, but voltage will be the different. Voltage will be the different, current will be the same. So now make sure. Now what is the conclusion? A galvanometer can be converted into ammeter. A galvanometer can be converted into voltmeter. When low resistance connected in parallel to the galvanometer, then galvanometer converted into ammeter. And when high resistance connected in series with the galvanometer, then galvanometer goes to the voltmeter. A voltmeter has high resistance because it's connected in the series, and ammeter has low resistance because it's connected in parallel. These two things are clear. One question I will give you, 2-3 questions that you have to solve. First one. Any 4 differences between ammeter and voltmeter. First one, you will read in the book, then you summarize the differences. What are the differences between ammeter and voltmeter? Second one, resistance of ammeter will be more than this one, resistance of milliammeter, resistance of micrometer. True or false? Check this one. Ammeter, A for ammeter, MA for milliammeter, mu A means micrometer. So this one, and similarly for voltmeter. Now see, what is third question? What is value of ideal voltmeter? What is value of resistance? what is value of resistance of ideal voltmeter. So these are the few questions based on the galvanometer. And now chapter 4 is the last now, and one more class I will see in numerical. Okay, try to explain some numerical problem from the moving coil what we read. So in the chapter 4 the modified syllabus is less, and according to that this is the last theory part of the chapter 4. One more video I will take on the numerical part, then we will start the chapter 5. And I will suggest you that you also start your study in parallel, write in notes, take the help from the books. And since chapter 4 means chapter 14 chapters are given in your syllabus, and syllabus these are the main chapters, so maximum portions are now going on. 2-3 chapters are there, those are reasoning based, so you have to utilize your time. Thank you, have a nice day.